Hi, today we're going to talk more about electron configurations and how they fit in with a periodic table. So if you think about hydrogen and its electron configuration, it has one electron, and that electron would be found in the 1s shell, according to the rules that we learned. It has an electron configuration of 1s1. Now, what if you were to go to the next element, to helium? Now you have two protons, you're going to have two electrons, and that second electron is also going to go into 1s. And so helium would have the electron configuration of 1s2. Now, if you think about element 3, lithium has 3 electrons. The first 2 are going to go in the 1s shell, as they did with helium. And you have one more electron. There's no more room in the 1s shell. It's going to have to go in 2s. And so its electron configuration is 1s2, 2s1. For beryllium, you now have an extra electron for a total of 4. Where is that extra electron going to go? It's also going to go in 2s. So beryllium is 1s2, 2s2. When you get to boron, you have yet another electron to place. And where is that electron going to go? It can't go in 2s because the 2s is full. So it's going to have to go in the 2p shell. So there's 1 in 2p. You add an extra electron to get to carbon. That's also going to go in 2p. So now that's 2p2, 2p3. For nitrogen, oxygen will have 2p4, fluorine will have 2p5, and neon will have 2p6. Now, if you then go to sodium, what's going to happen is that you're going to have an extra electron. The 2p subshell is full. So now that's going to have to go in 3s. So that's going to be 1s2, 2s2, 2p6, 3s1. So if you kept this up, you would see a pattern. And the pattern looks something like this. Everything in the first group of the periodic table, hydrogen, lithium, sodium, potassium, etc., has the last electron in an s shell, and there's only one electron in the s shell. Everything in the second group has the last electron placed in the s shell. So beryllium would be 2s2, magnesium would be 3s2, calcium would be 4s2, etc. The one exception is helium, which technically belongs there, and we'll talk about why it's placed over on the far right in the next video. But when I was a kid, the periodic tables actually showed hydrogen and helium together on the left, and hydrogen and helium together on the right as well. And that makes sense if you look at hydrogen and helium in two different ways. One is by looking at the electron configurations, and the other is by looking at the properties. Again, if we look at the rows or periods of the periodic table, which period you're in, at least in the S and the P subshell, tells you what your principal quantum number is. The first period, we have 1s. The second period, we have 2s, and over on the other side, we have 2p. Then we have 3s, and then 3p. Now let's talk a bit about the D. So the blue stuff here in the middle, what we call the transition metals, sometimes often called the D block, those are a little more complicated. If you think about what happens in the electron configuration diagram, when you filled the 3p orbital, you next go to 4s, and then from 4s, you go to 3d. So the first D shell you get to is 3D, so that's going to be 3D right there after 4S, which is how it is filled in on the electron configuration chart. After 5S, we're going to have 4D. After 6S, we're going to have 5D. And after 7S, we're going to have 6D. And what you can see here is that the principal quantum number of the D shell is always 1 less than the S shell that is right before it. But what about this stuff down at the bottom of the periodic table? Well, that is what we call the F block. And if we were to put those into the periodic table where they actually belong, the periodic table would look something like this. And it's pretty easy for me to show you this in HD format. But if I were to give it to you on an 8.5 by 11 sheet of paper, the writing would be super tiny, which is not very helpful. So usually what we do is we just put them down below with the understanding that everything in this row right here goes up to where it says 57 to 71, etc. Now I want to show you something about this block. Remember that we have 14 electrons in an F subshell. So let's go ahead and let's count what's down below. We have 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14. And you say, whoa, wait a second, there are 15 down here. What is that 15th one? Well, these 14 right here in each row are the elements where the F electrons are being filled in. These last ones are the Ds. Because remember, if you look at scandium, scandium would be 3D1. Yttrium would end with 4D1. What ends in 5D1? Well, the answer is lutetium, number 71. So just know that the element at the very end of this row at the bottom is actually a D block element. Okay, so I have yet to show you an electron configuration diagram that has F orbitals in it. But what you need to know is the F orbitals start in shell 4. So this would be 4F, and this would be 5F. And so the principal quantum number of the F block is always 2 smaller than the S block that precedes it. So 4F is right after 6S. 5D is after 6S. 5F is after 7S. That's 2 less than 7. 6D is after 7S. That's 1 less than 7. Knowing how the electron configurations correspond to the periodic table, what you can do is basically use the periodic table to write the electron configuration for any element. So we're going to start with osmium, which is one of my favorite freaky elements that no one ever talks about except me. So there's osmium right there. So basically what you want to do when you're writing the electron configuration for an element is start at the beginning and just think about what subshells you're going through as you move along the periodic table, and then just stop when you get to the element that you're interested in. So what I'm going to do, I'm going to start at hydrogen. So remember, this is 1s, and we're going to fill that whole 1s orbital. So it's going to be 1s2. Then we're going to go through 2s2. Then we're going to go through 2p6, completely filling the 2p orbital. Then we're going to go over here to 3s2. We're going to hit the 3p's, fill the 3p orbital, so 3p6. We're going to fill 4s, so that's 4s2. Now we're getting into the d's. We're going to go through 3d and filling that, so 3d10. Then we get to 4p's. The 4p6 is full. 5s, 5s2. All of 4d is full. All of 5p is full. All of 6s is full. Now we come to this spot, and this spot tells us we have to drop down and do the F block. So we're going to do 4F14 because that's all full. And then we're going to go through and we're going to start counting because we're now in 5D. 5D1, 2, 3, 4, 5, 6. So that's 5D6. And that is how you use the periodic table to figure out the electron configuration for osmium. As you can see, when you get down to the heavier elements, this becomes a pain. And so what we do for things like this is we write a shorthand electron configuration. So I want you to think what happens as you start filling shells. When you fill the entire shell with n equals 1, so you have 1s2, that's helium. When you fill the entire 2 shell, that's 2s2, 2p6, that's going to be neon. We could do the same thing for n equals 3. 3s2, 3p6 is going to bring us to argon. Now, note that we aren't filling the D shells, and the reason we do that is because the D shells fill up after we start going into n equals 4. So basically, if you fill the S and P shells, you end up with all the noble gases over on the right-hand side of the periodic table. So we're going to use these noble gases as benchmarks. So basically, what you're going to do is you're going to find the noble gas that is just before your element on the periodic table. You can't say the closest because sometimes the closest noble gas is moving forward. So go backwards to the noble gas right before your element, write the symbol for that noble gas in square brackets, and then write the electron configuration for the electrons you have to add after you get to the noble gas in order to get to your element. So I know that comes out a bit jumbled when I just say it. So let me show you with osmium, of course, because we've already done that. Okay, so we're going to start with osmium, and we're going to go backwards through the periodic table until you hit a noble gas. So you can just imagine walking backwards: rhenium, tungsten, tantalum, hafnium. Now, technically, now you have to drop down to the F block, so I'm going to cheat. I'm going to skip over to cesium, and then you can see that xenon is right before cesium, so that's what we're going to use. So xenon is what we're going to use, so we're going to write the symbol for xenon in square brackets, and what we're going to do, we're going to start at xenon, and we're going to add electrons to it until we get to osmium. So first we have to add the S block, so that's 6s2. Then we have to go down to the 4f's, and we're going to fill all of those in, 4 of 14, and then we're going to do D1, 2, 3, 4, 5, 6. So that's what it would look like in the shorthand electron configuration. So now we're going to talk about a term that gets used a lot, which is the valence shell. And the valence shell is the electron-containing shell with the highest principal quantum number in a particular atom. The reason I've underlined electron-containing is if you go and look at an electron configuration diagram, this particular one is for fluorine, it's not that fluorine doesn't have 3s and 3p. It absolutely does. But under normal circumstances, there are no electrons in the 3s and 3p. We're always going to look for the highest numbered shell that contains electrons, and that's going to be our valence shell. 1s is not our valence shell. It's part of what we call the core electrons. So now let's think about which electrons are in the valence shell of a few elements. So here's phosphorus. And you can see 1s2, 2s2, 2p6, 3s2, and 3p3 is the electron configuration. The valence shell is going to contain both 3s and 3p electrons because all of those electrons have the principal quantum number of 3. For strontium, you can easily identify that the 5s2 electrons are in the valence shell. There are no 5p electrons, so only the 5s electrons are in the valence shell. For molybdenum, now this is tricky because if you just look at what's on the far right of the electron configuration, you see 4d4, but 4 is not the highest principal quantum number that you can get electrons in for molybdenum. Again, it's the 5 shell that's going to be the valence shell. Finally, we have antimony. And what you can see here is the highest principal quantum number that you see is 5. So the valence shell is 5s and 5p electrons. And so even though you fill in the 4d electrons after the 5s and before the 5p, those are not counted as valence electrons. Remember, the principal quantum number tells us how far out we are from the nucleus. And so these valence shell electrons are actually the electrons that are closest to the outside world, if you want to think about things that way. And this is why they are so important, because it is those valence shell electrons that interact with their environment. So one last thing we need to get to in terms of electron configurations. From an energy point of view, the lowest energy electron configuration you can have is to have all of your subshells that contain electrons be completely full. But if you can't have that, the next lowest energy configuration is a subshell that is half full. So one of the things we talked about earlier is about the energy differences between these orbitals. So between the 1s and the 2s, there's a pretty big energy difference. If you go from 2p to 3s, it's a slightly smaller difference, but it's still substantial. But if you think about the difference between 4s and 3d, Remember, I said we fill 4s first because it is just a little bit lower in energy than 3d. But 3d and 4s are really, really close in energy. And that is important because an atom will sometimes shuffle one electron between 4s and 3d in order to get a more stable electron configuration. So basically, what you want to do is write the electron configuration the way you would predict, and then ask yourself, is it one electron away from a more ideal configuration? And that's almost always going to be one full subshell and one half full subshell. So for example, let's look at copper. And I'm just going to say straight out, it does have an anomalous electron configuration, but let's look at why. So we're just going to do shorthand here. And so we're going to start with argon as our noble gas, 4s2, and then if you count up, it's actually 3d9. Now, if you look at this electron configuration, the 4s shell is full, the 3d shell is not full, it's also not half full. And so what would happen if we moved one electron from 4s to 3d? What you'd get is argon, 4s1, because we've moved one electron, and 3d10. Now look at the advantages of this electron configuration. We have a full subshell, as we did before, but we also have a half full subshell instead of just a subshell with a random number. Basically, what we've covered in this video is how the periodic table tells us about the electron configuration of each element. The reason the periodic table has that wacky shape is because of the number of electrons you have in each subshell, and because of where you start getting different subshells like D subshells relative to the S's and the P's. I hope this was helpful, and I look forward to seeing you again soon.